All right. Prop 45 says to construct in a given rectilineal angle a parallelogram equal to a given rectilineal figure. Figure. I don't know why I said it that way. Okay, so, and this is a really interesting proposition for kind of a lot of reasons. I spent a lot of time looking at this one, not necessarily because the logic is so hard to follow or the math is so hard to follow, but more because, on the one hand, I wanted to figure out a decent way of sort of presenting this. And on the like in particular making the diagram as accurate as possible, which I think you'll see in a minute why that took me a little bit to figure out, but also just because I think it is a really ingenious construction. This is maybe the first time in the elements so far. We've done 44 propositions at this point, and this was the first one that I felt like I really sat in awe of just kind of how ingenious this whole construction is and the proof of the construction. So there's that. The other thing is that this proposition extrapolates. So the way that Euclid goes through this proposition is he does the construction for where the figure that we're given is a quadrilateral, but notice that it doesn't specify quadrilateral. It's any rectilineal figure. So even if you had something with 5 sides, 6 sides, 7 sides, assuming that all of the sides were just straight lines, this proposition allows you to construct a parallelogram and decompose, figures that have more than 4 sides. So we just kind of do the 4-sided case, and then the idea is which is not really stated anywhere in the proposition, is that, yeah, you can do this exact same procedure for figures that have more than 4 sides. And there is kind of an interesting assumption that is built into here, which sort of comes out in the very first line. Okay, so let's just jump into this thing. So here's our figure, ABCD. It's 4-sided. The angle E is what we're given, so we need to create a parallelogram, again, that is contained within angle E. So here's kind of what I've already done. Here's angle E down here, where I'm going to kind of build my parallelogram off of that. And the parallelogram has to have an area equal to ABCD. Okay, so the very first step is, in our ABCD, let DB be joined. So I'll just make it a dotted line to make it obvious that we're not working with sort of 2 separate figures here. So there's DB. And this is actually where the very first sort of unstated assumption comes in that Euclid sort of just glosses over. But today, I think mathematicians would look at it and go, wait a second, I think that actually needs to be proved. And the assumption or the lemma that I think would need to be proved before this is that this is always going to be possible, because the idea is that we have this rectilineal figure and we want to be able to join vertices of that figure to break it up or decompose it into triangles. So that is kind of like the unstated assumption, is that any rectilineal figure could be decomposed into triangles in that way, which is true. But it's not something that Euclid proved. It's something that he apparently just assumed was like, oh yeah, this is very obvious. Whether it was that he said he felt like it was just so intuitive that it didn't even need to be proved, or if it was that he recognized that he needed more tools than what we have at this point in order to prove it. Personally, I think it's probably the latter, that he realized there was like more of a pedagogical choice, that he realized in order for us to prove that every rectilineal figure could be decomposed into triangles, we need more tools than the 44 propositions we have at this point. That's what I kind of think. But in any case, maybe it was the case that he just felt it's really obvious. Yeah, you take any figure, any polygon, you can decompose it into triangles. And again, that is true. That's the big assumption that this whole proposition relies on. So in any case, we break our figure into 2 different triangles. And the very first step is that we're going to create a parallelogram. He calls it FH, which I'll label it once we get through it. But we're going to create a parallelogram right here in this corner that is equal to the triangle ABD and is contained in angle E. So that one's not too bad. it's kind of more the next step that things get a little bit complicated. So let me just try to quickly make triangle ABD in here. So the first step of that is to grab half of the base. So here is about half of the base ABD. I have like a stray mark in here. I just want to get rid of that. There we go. Half of that base. And then the next thing that we want to do is we need to grab the height of triangle ABD. So I grabbed half of the base, which I am taking to be side AB. So I marked off half of AB. Now I'm just going to kind of quickly recreate this triangle just so I can get the height of the triangle. Because what we need is we need to grab the height so that we can make a parallel line through that point. All right, so this will be up here somewhere. And then that allows us to make the parallelogram that is equal in area to our triangle. So yeah, kind of a lot of pieces I have to keep track of here. Okay, so what I just did was I found the height. This right here is the height, essentially, of triangle ABD. So I'll make a parallel through there. A line that's parallel to our sort of bottom line. Let's see here. Do it like this. There we go. And then the very last thing that I need to do now, let me erase some of these stray marks, is through this original line that I made, which is half of AB, I need to make another parallel. Parallel to that, and rather than making it perfect, I think I'll just try to eyeball it to try to save a little bit of time. Let's see, that looks pretty close to parallel, if you ask me. Okay, so I'll make these lines solid now, because this is going to actually be part of the construction. So here's our first parallelogram that we have made, which is equal to, oops, it's not quite right, side or triangle ABD. All right, and how do we label these points? Oh, and I guess I should start writing out some of the construction as well. I'll label these as, this will be H, but I need to be kind of careful. I'll write it maybe right here. It's H. Over here is going to be K. Up here is G, and this is F. Okay, so let me write some of these construction pieces down. I need to save a little bit of room. This is going to definitely be a multi-page proof. So first we will join DB in our original figure. We already did that. And then second we construct, and here we're just kind of shorthanding it. I'll call it FH. So FH is equal to triangle ABD, such that angle HKF is equal to angle E. And we have a proposition that was Prop 42 that allows us to do that. Okay. And then the next step is kind of the step that, like, the logic, again, the logic of it is not hard, but maybe trying to make the diagram accurate is a little bit trickier. So the next step is, I'll just read it, let the parallelogram GM equal to the triangle DBC be applied to the straight line GH in the angle GHM, which is equal to E. So in other words, the next step, which is really kind of the last step of the construction, is off of GH, we want to make another parallelogram, like between these two parallels, such that that parallelogram is equal in area to BCD, right? Not that bad. And that's just Prop 44 that gives us that. So as far as the logic goes, very simple, very straightforward. Just create another parallelogram using Prop 44. As far as actual construction goes, a little bit trickier. So here's what I will do. to try to, because I want this to be accurate. I could just make some line and say, okay, yeah, there it is. Boom. Okay, we're good. But I'd like it to be a little bit more accurate. So what I will do is kind of similar to what I just did, but I'm going to use prop 44, and you have to kind of construct this a little bit strangely, because if you remember from prop 44, you kind of create the diagram or the parallelogram sort of vicariously. It's not like you create it very directly. So what I'll do is, here is half of dB, where this time dB is going to be the base of BCD. And then moving down, I want to create the height of BCD. Okay, so I'm going to recreate this triangle again down here. I just need to make the height. Okay, so there's one side. Here comes the second side. Trying to move somewhat quickly so that it's not like a crazy long video, but it might end up being a sort of long video anyways, because some of the logic for the proof does take a little bit of time, a little bit of justification. Again, it's a really interesting, really clever proof construction, in my opinion. Okay, so now I've got the height, and the idea is I need to make a parallel through here, a line that's parallel to HK passing through here. I'll extend it out a little bit, so we're gonna need some room. Okay, so there's that. Erase a couple of these marks. So now I have essentially the height of triangle BCD, and from H to this little line right there, that is half of the base, so half of dB, which means if I continue this line down, and then I make another line through this point that is parallel to those lines, okay, so what have I done so far? This little segment right here is half of BD. These parallels have the height of BCD, which means that this parallelogram has the same area as BCD, right? So there's the parallelogram that has the same area as BCD, but I need this parallelogram, or the area of this parallelogram, to be up here, built off of GH. So I have to kind of continue this diagram. And the way that we do it is, again, super clever. Right, yeah, I don't need to say anything yet. So literally everything that I'm doing here is going to be contained in one line of proof, or one line of justification. So, okay. So I'll grab this point up here, and then I make I'm just kind of like doing things and muttering to myself here. Make a line through here. See where that meets at. And then very last thing that I do is I draw a line parallel to GH up through this point that I just found. Okay, and let me just fill in some of these lines now and explain what I did. Because now we have completed the construction. So basically what we did is, you can't really see it because I didn't add in some of the lines. Maybe I can add them in just to make it like really obvious. So there was that. And then we have this one as well. Oops. How on earth did I? Oh, right. Because I'm going from the wrong spot. That's why. Good thing I didn't make that line. Okay. So we have this parallelogram down here, this tiny little parallelogram down here that is equal in area to BCD. What I did then is I kind of completed the parallelogram so that right here, like this is the parallelogram that I'm looking at between these dashed lines. Some of them are solid, but here's the parallelogram. Then through there, we have this diameter that bisects it. And if you recall, we have a proposition which says that the complements about this diameter are equal. So these two parallelograms right here, they're equal in area, meaning that this parallelogram has the same area as this parallelogram, which has the same area as BCD. So that's like the end of the parallelogram. We call this L and M over here. Okay, so let me write out the justification, or the step that I just did, which is construct GM equal to triangle BCD. I should say off of GH, because that was part of it too. Off of GH such that angle MHL, is that right? And the angle GHM, right? Such that angle GHM equals angle E. That was everything for Prop 44. Okay. So then the claim, right, yeah. Next is claim is that FM is the required parallelogram. So what do we need to prove then? Well, a couple of things. The main thing that we need to prove is really just that FM is a parallelogram at all. So the opposite sides are equal and parallel. And there is some work that we need to do in order to prove that, because beyond that, the other requirements are kind of already built in there. Is that it's built in with angle E? Yeah, definitely. And that the area of the parallelogram is equal to the area of ABCD, which hopefully that's kind of obvious that we made that, that we constructed it that way. But we need to prove that FM is a parallelogram, which is not trivial. Okay, so we need to prove this. Okay, so, and I'll try to maybe write it a little bit quickly. We have that angle E is equal to angle HKF, and angle E is also equal to GHM. So, of course, by common notion 1, and I kind of already wrote it out, HKF is equal to GHM. So what does he say next? He says, let KHG be added to each. Well, then that means that angle HKF plus angle KHG equals angle GHM plus angle KHG. But what does that give us? Well, let's look at it. He says, but the angles FKH, KHG are equal to two right angles. So what are we looking at? FKH, FKH plus KHG are equal to two right angles. And this is because FK is parallel to GH. So, and that's by construction. Since FK is parallel to GH, by Prop 29, we get that angle FKH plus angle KHG equals two rights. Well, then that means that angle GHM plus angle KHG equals two rights. So again, just looking at the diagram, so GHM plus KHG. So kind of these two angles right in here are equal to two right angles. So we have a proposition that says something about that. Says Euclid says thus, with a straight line GH and at a point H on it, two straight lines KH and HM not lying on the same side make the adjacent angles equal to two right angles. Therefore, KH is in a straight line with HM. So I'll just say, and that was prop, what is it? 14. So by prop 14, KM is a straight line. Okay, and I'm going to need to pull up a new piece of paper here. Let's see, I still want that under. Okie dokie. So KM is a straight line. Great. Got a little more room there. Let's see what's next. And since the straight line HG falls upon the parallels. HG falls upon the parallels KM and FG. Notice we're not saying it falls upon the parallels KM and FL because we haven't even proved that FL is a straight line. But since KM is a straight line and it is parallel to FG with HG falling upon it, the alternate angles MHG and HGF are equal to one another. So that's prop 29 again. So by prop 29, angle MHG equals angle HGF. And again, this is since KM is parallel to FG. Okie dokie. Well, what next? He says, let the angle HGL be added to each. So then, come on, angle HGL plus, what was it, MHG is equal to HGL plus HGF, angle HGF. Right, therefore the angles MHG are equal to the angles, yes, right, we have that. But, what does he say? He says, but the angles MHG and HGL are equal to two right angles. So, MHG, HGL are equal to two right angles. And that's because HM is parallel to GL. So, since HM is parallel to GL, and that is by construction. Right. We get that by, let's see here, MHG, HGL, and it's not cited in here. MHG and HGL are equal to two right angles, so MHG, HGL. I think that is also prop 29 again. It's either 28 and 29. They're like really similar. I think it's prop 29. By 29, angle MHG plus angle HGL equals two rights. So angle HGL plus angle HGF equals two rights. So HGL and HGF. So for the same reason, then again by kind of like earlier, prop 14, we get that FL is a straight line. Okay, so we've proven that KM is a straight line. We've proven that FL is a straight line. And we just need to prove opposite sides are parallel. So how do we do that? We say since FK, straighten my papers out here, since FK equals HG and FK is parallel to HG. And HG is equal to LM and parallel to it. It follows that FK equals LM and is parallel to it. Where do we get that from? We got that from Prop 34. I guess it's actually kind of two, right? So Prop 34 tells us that FK equals HG and is parallel to it. So I'll say this is from Prop 34. And that's also, yeah, KF is equal and parallel to ML by Prop 30. So kind of two lines of reasoning in there, Prop 34 and Prop 30. All right, we're almost there. Then we have that KM and FL join FK and LM at their extremities. Which means that FL is equal and parallel to KM. So yeah, hence KM and FL are equal and parallel. And that was by Prop 33. So KFLM is a parallelogram. So that's like the big piece of it. We have a little bit more by construction. Am I still on the page? Not quite. Let's see if I can maybe do this. By construction, angle FKM equals angle E, and FH equals triangle ABD, GM equals triangle BCD, so that KFLM equals ABCD. We did it. QEF. So yeah, there it is. Right, I think that's like a really just a crazy, ingenious, innovative proof. And it took me almost a half hour to get through it. I hope that you enjoyed that. See you next time.